Hello and welcome to another R Gallery tutorial. In this video I will show how to create a density plot in R by using the ggplot geom density function. Let me start with a quick summary of what to expect in the next minutes. We start with a basic density plot and show how this is different from a histogram. And this is really important when you have two distributions with different sample sizes, because the density chart will make the area under the curve for both of them equal to 1, but more about that later. Then we will talk about how to change the resolution of the curve with the bandwidth argument, or BW. Next I will show a cool trick to mirror a distribution by setting the Y argument to negative density. Of course, we will also go into the topic of multiple distributions and how to visualize them. For example, we can make them more transparent or have them fill out the complete chart area, aka making them add up to 100%. We can also stack them on top of each other or spread them into their own plots with facet wrap. Then I will also describe how to do annotations by adding text, and I will show how Marginal can be used to add the distribution to a chart in the margins, either as histograms, density plots or box plots. And lastly, I will link to a beautiful example I found during the 30-day chart challenge that combined density plots and box plots for 3 different disciplines, showing the difference between female and male powerlifters. This will be the second tutorial regarding the visualization of distributions, and as always I will mostly be following the examples from the R graph gallery. Link in the description in case you want to try out the R code by yourself. Let's get started with the tutorial. In order to show the difference between histograms and density plots, I created a data frame called test with 2 columns, volume and group. The value column holds 100 randomly generated data points from a normal distribution with the mean of 5 and 200 data points from a normal distribution with the mean of 10. The second column then just repeats A 100 times and B 200 times, so that we can identify the first distribution A and the second B. With view, you can look at this newly generated data set with the first 100 A values centered around 5 and the next 200 centered around 10, with a standard deviation of 1 by default. To generate a histogram with ggplot, it asks for the dataset and then the mapping, and then you simply specify the data as test. And the mapping for a histogram only needs one variable for the x-axis, which comes from the value column. And then you add the geom histogram function. If you're more familiar with the ggplot function already, then you would probably save a lot of time by just piping the dataset into the ggplot function and then follow up with the aesthetics mapping and specify the value from the dataset you want to plot. When we switch the geom histogram for the geom density function, we get a graph that looks very similar to the histogram, but now shows a curve with an area adding up to 1 or 100%. But there's one important difference when we create density charts for the 2 different distributions A and B. When we set the fill argument within ggplot to group and then show the histograms, you notice that histogram B has higher bars than histogram A, because here the sample size was twice as big as the sample size for A. But when we do the same thing for the geom density, this difference disappears, because now again each area has to add up to 100% or 1. Imagine a normal distribution. No matter if you base it on 100 or 1000 values, you will always get the same density distribution, with 68% of values falling within plus and minus 1 standard deviation. If you don't fill the area but use color to just color the outline of the distribution, you could actually calculate the area of each rectangle and then add them up to see that you would reach a total sum of 1. Let's talk about the function's arguments next. I will now explain the bandwidth argument, the adjust and the kernel. In geom histograms you can specify the number of bins you want to see for your distribution with the bins argument. When you set it to 10 you will get 10 bins showing the distribution. When you go to 50 it will look more fine-grained, or you use the bin width argument, where you can increase it to 2 or decrease it to 0.1 or any value you wish. With geom density you have 2 options. You either specify the bin width, where higher values will decrease the resolution of your distribution and lower values will increase the resolution. And the second way is to use the adjust argument within geom density. The geom density by default tries to fit a Gaussian kernel, so a normal distribution around the data, and with adjust you can specify the standard deviation of this kernel. 2 will increase the standard deviation and values below 1 will decrease it, giving it a higher resolution. Speaking of kernels, there are 7 different to choose from for the geom density plot. I created a visualization of them, and now that we click through them they all look pretty similar. with only minor adjustments. If you don't specify it, Gaussian will be the default. A good first place to learn more about kernels is the Wikipedia page, Kernel Statistics. Here you find a nice overview about functions that are commonly used as kernels, for example the Gaussian or a uniform or triangle distribution. It also has a nice overview of the formula used. This one might look familiar from the normal distribution or the Gaussian kernel. So the first example on the rgraph gallery from Jan Holz comes from a dataset with 10,000 prices for Airbnb apartments on the French Riviera. If we load it with read table from the raw data website and filter for prices below 300, we get the following density distribution with the color for fill and the color for the color outside and an alpha making it a bit see-through. If we want to increase the resolution, we simply specify the bandwidth as 2. And if you don't specify the color argument, by default it will be black as the outline. For the mirror density plot, I created a dummy dataset with a default mean of 0 for one distribution and then a second one with a mean of 2. You specify the dataset within ggplot and then have two different density functions for the top and the bottom. On the x-axis you put variable 1 or variable 2, but now for the y-axis you have to be careful to specify density in this format and minus density for the bottom part. geom label simply puts a rectangle with a variable value that you can specify as label, and you can select the color for the text and the outline. In the next part I want to show how you not mirror different distributions but overlay them, and for this we use the diamonds dataset that's already available within R. It shows over 50,000 diamonds and their price based on different variables like the weight and carat, the cut, the color, clarity and depth. We will only focus on price and cut in the next examples. But keep in mind that the price is also determined by the weight and the clarity and color. This is how the density plot would look if we don't specify the cut as groups, would just be one distribution. But the moment you tell ggplot that there is a group to be expected based on cut, it will start creating density plots for each of the 5 different cuts. You can now color the line of each individual cut group by specifying the color argument within the aesthetics mapping for geom density, and you could have saved a little bit of code by already putting this into the original aesthetics mapping. Because if we do the same for the fill argument with cut and don't do anything special for geom density, this is what we would get. So now that color isn't specified, it will be black for each of the different cuts, but the fill color will be different. Now you can already see that this is not optimal because some distributions make the underlying distributions invisible, but when you specify alpha within geom density, you can make them see-through. There are 2 other ways to get around the overlay of different distributions. You can adjust the position argument, for example to fill, and then have each distribution add up to 100% in total. And when you use stack as position, the distributions will be stacked on top of each other. This already makes it a little bit easier to judge how the distributions are differently shifted towards each other. But what you can also do is simply use the cut within facet wrap to make one graph for each different cut, and now that you have the cut labeled on top of each distribution, you won't need the legend anymore, and with theme legend position equals none you can get rid of it. And I think this is the best way to visualize the different cut prices from the diamonds dataset with density plots. For the annotations example, we load a dataset where respondents were asked what probability they assign to certain text values. So almost certainly had very high probabilities, probable, bit lower, about even, centered around 50%, and almost no chance had mostly single-digit probabilities. We can create the density plots for these 4 different distributions by specifying color and fill based on text. With the labs function, you can label the y and the x-axis very conveniently, and we don't have to use the legend when we annotate these distributions with text. A quick way to do this is by creating an annotation data frame. So when we know the name of this distribution being almost no chance, about even, probable, almost certainly, we can put the x positions at different values and the y position at different densities. So now to include the text annotations within the plot, all you have to do is to specify geom text. You give the x and the y values as specified in the data frame. Label is the argument that asks for the text to be plotted. The color will be also based on the text, making it similar to the color we used for the distributions. And then we have horizontal adjustment adjustments and the size for the text, which then gives quite a pretty looking graph. And it's actually quite interesting when you talk to people that aren't too familiar with statistics. They might have very different assumptions about terms like probable or almost certainly. You might be familiar with the empty cars dataset, where you can plot the weight of different cars against the mileage, so the miles per gallons they would drive. And here we color the cylinders 4, 6 and 8 and have a size of 2 for the geom points. And now with the GG Extra package, you can add marginal distributions of different types. So the GG Marginal function can add histograms or density plots, where you can then see is it a normal distribution of weights, and you can also add a box plot. The last example I want to show is a combination of density chart and box plots that you can do when you load the pupillometry R package, because there is a function called geom flat violin that can be easily combined with box plots. And I came across this example during the 30-day chart challenge that I followed on Twitter, where one user named Chian Bladen made the following visualization showing the overlap and differences between male and female powerlifters for 3 different disciplines like squat, deadlift and bench. Interesting to see that there is some overlap, but it's also very difficult for the best performing females to beat the average male powerlifter. I would personally be around here for the bench, a little bit here for the deadlift, and for squat way below 100 kilos. The code is actually not that long, it's pretty clean, some data changes from wide to long format, but then for plotting it's simply the function with some nudge argument to put it into a different axis, and then you add a geom box plot, and the rest is basically some cleanup steps for legend position and axis titles and the grid layout to make it look as pretty as it came out. That's the end of this tutorial. I hope you learned a lot about geom density plots and are able to use them by yourself now. The next tutorials will be about box plots and histograms. So subscribe to the channel if you want to be notified when they are uploaded. Give it a like if you find this content useful, and see you next time here at the Data Digest.